Now we'll move to the next proposition. Suppose we want to convert the following three analog signals into digital ones with a sampling rate of fs equals to 10 hertz. Okay, 10 hertz. We'll have a look to three signals. 3 hertz, 10 hertz is sufficient for it. 7 hertz, it's not. 10 is less than 2 times 7, which will be 40. And what about 13 hertz? 13 hertz needs a frequency rate of more than 26 hertz. But we are going to use 10 hertz. So for these two cases, we'll have aliasing. The goal of this proposition is to show how the aliasing will act. Okay? But for this first one, we will have no problem. We substitute t equals n times ts. So we'll have x1 of n will be equal to cosine of 0.6 times pi times n. What about the second one? When we substitute t equals to n times ts, we'll have x2 of n is equal to cosine of 1.4 times pi times n. We should stop here. We have a cosine exceeding pi 180 degrees. Okay? So, we should write cosine of 2 pi minus alpha equals to cosine of alpha, or in this case it will be cosine of 2 pi n minus 1.4 times pi times n, or leading to cosine of 0.6 times pi times n, which is similar to the first one. Okay, so we have lost information. Now, what about the third one, x of 3, which is equal to cosine of 26 times pi times t, which will lead to cosine of 2.6 times pi times n, and finally cosine of 0.6 times pi times n, just getting rid of 2 pi n. Okay? Now have a deep look at the results. The three results in discrete environment are the same, but we know that in reality, and when we started processing, they were different in analog time domain. So something has happened. Now we want to discuss about it. Due to insufficient sampling rate, this ambiguity arises, which is called aliasing. Note that the maximum digital angular frequency, or omega, is equal to pi in digital environment. And if omega is greater than pi, aliasing will happen. Please write it down. Now, if we decide to convert back these three signals from digital form into analog, taking into account that t is equal to n times ts, so we will have n is equal to t times fs, or frequency rate. Therefore, we will have x1 of t is equal to the second one and is equal to the third one. All of them are equal to cosine of 3 hertz or 6 times pi times t. It means we have lost the information for case 2 and 3. That's it. But the first one is a healthy processing. So what's the solution? This time, we decide to increase sampling rate. If we choose TS to be equal to 0.02 or say it 50 Hertz as sampling rate, there will be no aliasing because 50 is greater than the maximum frequency existing here for 3 cases. So again, repeating 3 signals in time domain and analog form will lead to digital counterparts which you are looking at. x1 of n will be cosine of 0.12 times pi times n, and the second one 0.28, and the third one 0.52.